so far we have seen that induction means, or electromagnetic induction means, production of EMF due to change in flux. Now we shall take it in two parts, self-induction and mutual induction. Now see, in self-induction we have just one coil. If I take a coil, connect it to a battery and a key. Now when I press the key, then current starts flowing in this. Starting, current is 0 and then gradually it increases and maybe it reaches up to I. Now when this current is increasing, this coil has increasing current. Increasing current means the flux will change. We know that flux is B into A and B depends on current. So when the current is increasing, magnetic field is increasing, which means the flux is increasing. So it will oppose the growth and there will be an induced EMF. Induced EMF will give rise again to a current which has a tendency to oppose the growth. So due to this tendency of opposing the change in current, this current will take some time to reach its maximum value. We can compare it with inertia that we studied in mechanics. So we can say all coils have electrical inertia. They have a tendency to have whatever current they have. It means any effort to change current will lead to opposition of this current. So if zero current, it tends to have zero current only. So when we start the current, it will oppose it and there will be an induced EMF. If the current is flowing through it, I switch it off, again there will be an induced EMF. And this time in the direction of the EMF. So this inertia is always there. We can call it electrical inertia. And how much is the induced EMF? Induced EMF, we have already done it. It is d phi by dt. With a negative sign tells us about the direction of the induced EMF. Now, flux is proportional to current. Right? When current increases, the magnetic field increases. Magnetic field increases means flux increases. Now this constant of proportionality here is called the coefficient of self-induction. It is the coefficient of self-induction or simply self-inductance. Self-inductance or coefficient of self-induction. It has a unit Henry or Weber per ampere. Now, we are saying it is electrical inertia. We know the mechanical inertia is measured by, we can recall all those expressions. There is a force, mass into acceleration. Right? Force is mass into acceleration. So whenever the velocity changes, it means there is a force and this is the inertia that opposes this variation in speed or velocity. Here we have induced EMF and this is the inertia. So similar expression. It is the electrical inertia or Li is n phi. And the same thing, we can compare these two expressions. One, this is equal to d phi by dt and we have n phi as Li also. So I can write that induced EMF also as minus d by dt. Here we have n phi. Phi is for one turn. If there are n turns in the coil, it becomes this, and minus d by dt Li. L does not depend on time. This inertia, this is determined by the geometry and the medium. Okay, so this is we can define this inertia from here. It is equal to the induced EMF produced when the current is changing at the rate of 1 ampere per second. Okay, so see it again. Whenever the current through a coil changes, there is an induced EMF, and if it is closed, there is an induced current which opposes the variation. I'm saying variation because when we switch it on, it opposes it. So the EMF, induced EMF, is opposite to it. But when we switch it off, the induced EMF is actually in the same direction, in which and the current, induced current and the current due to this battery, they flow in the same direction at the time of breakup of the circuit, because it tries to maintain that. So it's a sort of electrical inertia. Just like the inertia in mechanics, I told you their mass determines inertia. Every effort to change the velocity is opposed by the inbuilt tendency of the body, and that tendency is measured by mass. Here, any effort to change the current through a coil is opposed by it, and that tendency is measured by the self-inductance. It depends on the geometry, it depends on the medium. Using Faraday's laws, E is equal to d phi by dt, we have written n phi is Li, so I can substitute this Li here. L does not depend on time, can be taken out of the differentiation sign, so it becomes is equal to L di by dt. Minus sign, we have done it earlier, it tells about the Lenge's law. The direction of induced EMF is such that the current produced by this EMF opposes the cause which produces this. Okay, now I am telling you one experiment, and then we shall do the self-inductance for specific coils. Okay, how to demonstrate this self-induction, that it is actually happening. Now see, if I take a coil connected to a battery and then again a key, and let me connect a neon bulb here, and a battery maybe 9 volt. I'm showing you an activity in which the this battery has been taken of 9 volt, then there is a coil and a neon bulb which can be lighted with much higher voltage than 9 volt. Okay, so what will happen when I switch it on? The bulb will not light because there is not enough voltage across it. Maximum voltage is 9 volt. But when we break this circuit, induced EMF is produced which is added to this. So total EMF is increased in a way in the circuit, and the bulb lights up. Now I am showing you this activity. Please observe it very carefully. Time of break, actually the induced current is more in the circuit. So if I give you a numerical and ask you calculate the time, if its resistance is R, what is the current in the circuit? So then this is V by R if there are no inductive effects, but otherwise at the time of switch on the current will be less than this because it is opposed. Right, so it is V minus L di by dt by R. Right, but when we switch it off, then it is V plus L di by dt upon R. Reason, because di by dt is negative. When we switch off, The current is decreasing with time. So the net EMF is increased and the current is increased. The same thing happening here also in the activity that I am showing you. When we break the circuit, the bulb is lighted, otherwise not. Okay, now how to find out the self-inductance for given coils. I am giving you an example of solenoid. It's very simple actually. We have to just substitute. Let's take a very long solenoid, infinitely long solenoid with a cross-section area A, number of turns N per unit length. So what will be the value of phi? B into A. And what is B? Mu naught Ni into A. So that's it. We need to just substitute. N, phi is BA and B is mu naught Ni. A is equal to Li. So what is L? It is mu naught N A or mu naught N square A by L, where I have taken this N as number of turns per unit length, so I have just substituted this. So see now, self-inductance is proportional to the area of cross section, inversely proportional to length, proportional to N square, and mu naught also. So if we put soft iron inside the solenoid, so it will be increased. Now this will be the self-inductance, right? Self-inductance, and it is equal to the induced EMF produced when current is changing at the rate of 1 ampere per second. So it means if we want more induced EMF, then we need to increase the value of L, which can be increased by these factors. Putting the soft iron core, increasing the number of turn, increasing the area of cross section, or reducing the length. So that's all in this topic of self-induction.